Okay, so it's my pleasure to introduce Nigel Pynn-Coates, and he will talk about asymptotic valued differential fields.
Okay, thanks. So thank you for having me, everyone. This is really a talk about valuation theory of differential fields. If I read the schedule correctly, Martin Hills was here recently, like last week. So like any two good talks in valuation theory, we'll have different notation. But that's how it will go. And so I guess I'm going to tell you about a few theorems that are generalizations or analogs of valuation theory theorems in the setting of asymptotic valued differential fields. So in some sense, asymptotic, I'll argue, is like the right condition to place on the interaction between the valuation and the derivation, at least if we want to do some kind of valuation theory. It also has some, all fields are characteristic zero in this talk, okay. It also has some motivation in terms of Transseries and Hardy fields, which I'll say a bit about now. So I'm not sure how familiar people are with these things, but I just, by a Hardy field, mean a field of germs at infinity of real valued functions that's closed under differentiation. So germs, of course, I mean they're defined on some interval a infinity, and they're equal, or equivalent if they're eventually equal on some ray b infinity. And closed under differentiation, I mean, again, I do everything up to, increasing my a. So it's eventually differentiable and needs to form a field. So you don't get any kind of oscillation or things like that, infinitely many zeros or cofinally many zeros in R. So what are some examples? Well, kind of basic examples. Q, Rx, R square root x, you can add exponentials and logs. Hardy's LE functions, which essentially are like, as he says, you build a field using the basic algebraic operations and en log, by which he means, field operations and nth roots, and exponent log. And he thought, this kind of, the history goes back to Dubois-Reymond and other people in the 19th century as well. But he was kind of, trying to study rates of growth at infinity of real valued functions. And so he thought these LE functions kind of contain all the rates of growth that we would naturally occur in analysis, was his view.
Could you clarify, so did he allow to make composition of them? Like E of x or something?
Yeah, so you can apply, exponentials to things, yes.
Okay.
Logarithms. I'm not sure if he allowed arbitrary composition or whatever, but I guess it will. I guess it will follow from his but this will be a problem why we need Transseries, because there are some issues with composition.
Yeah, that's true.
Yeah. So if you're a model theorist, also in any O-minimal expansion of the real field, the definable unary functions form a Hardy field. There's a natural ordering on the germs, just by saying it's positive if it's eventually positive, and because it's a field, it will be eventually positive, or eventually negative, or eventually zero. And so from this ordering, you induce a valuation. And so your valuation ring is like the set of bounded functions, in this case literally bounded functions, but in the talk there might not be some ordering later, but you should still think of this O as bounded functions. Here it just literally they're bounded by some real constant eventually. And one other useful fact that will show up later or motivate the condition of being asymptotic is this L'Hopital rule at infinity that the limit of the quotient of two germs is the limit of the quotient of their derivatives. Okay. So what are some problems? Well, lots of kind of closure properties that they lack, including, for instance, Hardy isolated this particular function that doesn't have an inverse in his field. He couldn't prove it at the time, but he identified it as something that would be problematic. And if you think about what the rate of growth of the inverse of this should have, you can kind of convince yourself that it's reasonable that it shouldn't be in his field. The one way to rectify this is to create this field of logarithmic exponential Transseries T, You basically, I mean, the rough idea is you start with real power series, and you close under exponentials, logarithms, composition, and nth roots, and etc. I mean, it's a long inductive construction, of course, but you obtain some actual object that is lots of closure properties. It's real closed as a field, closed under exponentiation, integration, composition, compositional inversion, and resolution of certain other kinds of ODEs. So here's an example just to give you a picture of what one of these things look like. So they all have, they have some length of some countable ordinal. In this case, it's omega plus 1 because we have e to the minus x at the end. But you can compose them so you have e to the x plus e to the x over 2 plus e to the x over 4 plus dot dot dot. This first term is the leading term. You have minus 3 e to the x squared. You have real powers, logarithms, etc. And you order the terms in the natural way. So x, you should think of as going to infinity. E to the x goes to infinity, faster. And so it's arranged in that natural kind of ordering of the monomials here.
And what's the meaning of certain ODEs?
Yeah, that's a good question. Okay, I don't want to get into it right now. Is that okay? Okay. Doesn't answer your question at all, but. Yeah. I'm not really, okay. So the truth is, my advisor has, done a major project on Transseries. I have read some of the work, but I'm not an expert exactly on all the kinds of properties that they have.
My question was whether, so who chooses that? There exists, or what is it? So T depends on that, or?
Oh, no, no, this just falls out from the construction, that you can show that certain classes of ODs have solutions.
Classes of, okay,
yeah,
certain
yeah.
classes of.
Yeah, but it's not like it's not part of the construction, say.
Okay.
Yeah, if that answers your question.
Mm-hmm.
Yeah, it also satisfies some analog of L'Hopital's rule at infinity, a kind of valuation theory analog that I'll say later. And some kind of Transseries were introduced by Ekal in proving, Dulac's conjecture, and also Dahn and Göring in studying models of the real field with exponentiation. And then Matthias Aschenbenner, Lau van der Dries, and Joris van der Hoeven more recently gave an axiomatization of this field. They show that it was model complete in the language of ordered value differential fields. And when they added 3 extra predicates, well, doesn't have quantifier elimination in that language, but when you add 3 extra predicates for certain cuts in the field, you get quantifier elimination. Okay, I guess I'm a model theorist, so these...
Excuse me.
Yeah.
So do this correctly as you have not yet defined the valuation on this, right?
Yeah, I have not really defined anything on it, I guess, but I define the valuation by saying A is, dominates B if the leading term dominates the leading term. The leading term of A dominates the leading term of B.
Okay.
And you just define the ordering on the leading terms in the kind of obvious way after,
Okay.
Yeah.
Okay. Thank you.
But it's also, because it's an ordered field, it's also induced from the ordering. Just, if you...
Mm-hmm.
But you have to define the ordering. But the ordering is just, it's positive if the coefficient of the
leading terms.
Exactly. Everything is defined leading terms by the leading terms. Yeah. Yeah. So I'm a model theorist, so I guess why would we want to do valuation theory of differential fields? Why do we want these valuation theory theorems to hold in the value differential setting? Maybe we want to prove something like this for value differential fields or a certain class. So this is, kind of a well-known theorem of Ax-Kochen and Ershov that says for 2 Henselian valued fields, they're elementarily equivalent in the sense that, they have the same first order theory, maybe you take the language to be just language of rings plus a predicate for the valuation ring, say, if and only if their residue fields and value groups are. And okay, I will define all these things later. So these are two simpler structures that are associated to the valued field. You should kind of maybe think of a valued field as the little k1 being the the like coefficient field of coefficients, and the gamma as being like the group of rates of growths. Yeah. And so a general principle in valuation theory is to try to understand the valued field in terms of these two simpler components. And so this theorem says under this Henselian assumption and everything's characteristic zero, as I said, you can do this in a first order way. And some tools from valuation theory that you use in a proof of such a thing is that, well, you have some uniqueness of certain kinds of extensions, you have some equivalence of henselianity, which is a first order property about lifting zeros, to some non-first order property about maximality in a certain class of extensions, and then henselizations, which are Henselian extensions with a kind of semi-universal property. I will define all of these things in the differential analogs of them later, but I just want to mention I'm going to show you three of these kind of analog theorems, and I want to argue why maybe a model theorist might care about these analogs. Okay, so a valued field for me is a field with a surjective map V to this ordered abelian group gamma and this symbol infinity, where infinity is bigger than everything in gamma, and you extend the addition in the kind of natural way. And you send 0 to infinity, and it's a group homomorphism from the multiplicative group of k to gamma, and it satisfies this strong triangle inequality. So the valuation of x plus y is at least the minimum of the valuation of x and the valuation of y. So you should think of, bigger valuation is closer to 0. And negative valuation is, infinite. Positive valuation is infinitesimal. Yeah. So because of this kind of, it's kind of annoying to wrap your head around, because this standard definition in valuation theory, everything is kind of flipped in terms of how you would like it, of course. So I'm going to use this other notation, which I think at least hard to use some of these terms as well, at least this dominant symbol. So I'll write f bounded by g, or dominated by g, if the valuation of f is at least the valuation of g, and similar with strict domination. So you should think of, f bounded by g, saying that f grows at most as fast as g towards infinity. And so then this O is the set of elements that are bounded by 1. So you should think of them, again, as big O of 1, hence the notation. They're bounded, and it has a unique maximal ideal little o, which are the elements that are strictly bounded by 1, that are, infinitesimal. So this k, as on the previous slide, is the residue field, is just the quotient field there, and it's like the field of coefficients in some sense.
So for actual functions, strictly bounded by 1 means tends to 0 at infinity, or means tends to something less than 1 at infinity?
Strictly bounded by 1 in the sense of Hardy fields means goes to 0.
Oh.
Yeah. Yeah. Okay. Yeah, this slide, you don't need to pay attention to, really just some notation, of course. My derivation del f prime for del f, c constant field, and k braces y differential polynomial ring. So what kind of condition can we place on the interaction between the valuation and the derivation? Well, you might want continuity, say. So there's from evaluation you get some topology on the field, which I won't go into, but you would at least expect the derivation to be continuous with respect to the valuation. I'm going to, in general, assume a little bit more that, the derivative of an infinitesimal is an infinitesimal. This is, in some sense, not in some sense, it's almost equivalent to continuity. Continuity just says there exists an A such that, derivation of O is contained in A. times the derivation of O. So you're allowed one scale of the derivation that's equivalent to continuity. But in any case, I mean, it's not really too relevant. The main thing is this property. And what does it do for you? Well, it gives you continuity, but also it implies that the derivation applied to the valuation ring is also maps into the valuation ring. So you get an induced derivation on the residue field.
And back in the world of functions, this means that if a function tends to 0, then its derivative should also tend to 0.
Mm-hmm.
Again, in terms of functions, so in Hardy fields, this little k is constants, right?
Yeah,
so it
just the reals or the q or whatever. Yeah.
So so this is not. So this delta will be just 0. Okay.
Yes.
Okay.
Mm-hmm. Yeah. So this is. Yeah. So the Hardy field setting is Yeah, this is where we will diverge later because, as you say, it's true and important that the induced derivation on the constant field of a Hardy field or an H field is trivial. But in this setting, it will not be trivial. So that's where kind of the intuition from Hardy fields will not, carry over.
And for the Transseries, it's also 0.
Yeah, it's also, the constant field of the Transseries is also R.
Mm-hmm.
So what would be an example where it's non-trivial?
Yeah, so one example that you can come up with is, say, if you start with some differential field and you take just power series over that field in some ordered abelian, the exponents being in some ordered abelian group, and you define the derivation like term by term.
Mm-hmm. So just Laurent series.
Yeah. Sure.
Okay.
Laurent series.
But the derivation doesn't interact with any variable at all.
Yeah, yes, it does not. I mean, okay, there you can extend it in more clever ways, but this is the basic kind of that was studied by Scanlon earlier. Yeah, but in general, those are not. Yeah, in general, those will not be asymptotic. So, in some sense, I've kind of dodged your question.
Mm.
Yeah, but I mean, the examples that I really have in mind are. Like you take Transseries and you modify the derivation and coarsen the valuation a little bit. So you take Transseries and you do some kind of operations to study certain kinds of subfields with modified valuation and derivation. And then you can get actually a non-trivial derivation on the residue field.
Okay, so examples you're interested in come actually from Transseries.
Yes. Yeah.
I see, okay, good.
Coarsen means bigger ideal, smaller ideal.
Yeah, it's... I don't want to answer because I'm going to say it wrong, but
Yeah.
Yeah, it's always
But
confusing
somehow you
in terms
multiply
of the...
by less, so some derivation is left.
Yeah, exactly. You have a... yeah, okay. Because there's the valuation ring and the... you should get a bigger residue field. Yeah. So So a bigger ideal, yes. Yeah. Okay, so I'm going to be considering various extensions. So let me just say that all the fields that I'll mention have small derivations. So extension will just be in this sense value differential field extension with small derivation. And then this maximality property before was meant or will mean in the differential setting, maximal means has no proper immediate extensions. Oh, did I not define immediate? Okay, sorry. I must have deleted that or forgot it. So immediate means you have the same value group and residue field. So it's like you have the same set of coefficients and rates of growth. And so maximal means, up to those two choices, you don't have can't add any more.
It happens that you have a differential valued field, and if you forgot the derivative, you could have an immediate extension.
It could be,
but with the derivative you cannot.
So, so let me think for a second.
Well, how do you forget a derivation if you are talking about always small thing?
Yeah, so...
Small thing, derivation.
Oh, I see. So maybe another question is, could it be that you have an immediate extension that allows you to extend the derivation, but it can't possibly be small?
Yeah, so the way, I guess, to answer your question is you have to show that maximal immediate extensions, in this sense, are actually spherically complete as valued fields.
Yeah.
And then they're maximal as valued fields.
Yes, so that's what I was asking. Is
Yes.
that true?
Yes, that's true.
Oh, okay.
So in this sense, in this
Okay.
sense with small derivation, that's true.
Okay, interesting.
And then the differential algebraic analog is just saying no proper differentially algebraic immediate extensions. Yeah, I will shorten differential and differentially to D here. I don't know if you guys hate that or if that's standard, but anyway.
Can there really be a difference between those two?
These two?
Yes.
Yes. Yeah?
Does the residue field and the value group has anything to do with it being small?
I mean,
What's the question?
Maybe a more precise way
I mean-
to ask the same question is considering the pairs that you could get as a residue field and value group, can all of them be realized with a small derivation?
Yeah, okay,
Okay.
yeah, better.
yes.
Okay.
But I mean, you can always do some kind of
Stupid Hahn field?
Yeah, you do a Hahn field.
Yeah.
That's the answer to that question. But I mean, yeah, in the asymptotic setting that I will tell you about,
But your theorem earlier says that the value differential field is determined uniquely already.
Ah.
I mean,
so what it said was as a valued field.
But you already
Right.
assume that you have some background theory. So if we're going to prove a similar result, we're going to say, suppose you have two small differential
Yes.
value fields with the same
so,
residue. With the
but
same.
then you don't need to add anything to the residue field, I mean, property to the value field and the value group?
Well, we'll see. We haven't
Okay.
seen the new theorems yet, right?
All right.
Yeah, spoiler though, I do not have an Ax-Kochen Ershov theorem to tell you. So just, sorry to disappoint.
Do you
But
have counterexamples?
no.
Okay.
In the asymptotic setting, whether you have small derivation is actually determined by your value group, though. So under the assumption of asymptotic that I will define, it is determined by your value group,
Okay.
or by your value group with some induced structure from the derivation, really. Yeah, not just by the value group. So let me define this key property of differential Henselian. So it says that for all differential polynomials with bounded coefficients, if the degree of p bar is 1, and by p bar I mean the map down to the residue field, right? So I forget about all the infinitesimal terms. Then if it looks linear, so it's kind of quasi-linear in some sense of quasi, then you should have a zero that's bounded.
So, but like, it doesn't look like usual Henselian, right?
So this is equivalent. If you actually just change the braces to ordinary, this is an equivalent definition of Henselian. It doesn't maybe look like the one you remember, but you can.
Yeah, that's true.
So I mean, the trick in this theory was to figure out which of the many equivalent definitions of Henselian is, the right one or a right one. So I mean, Tom Scanlon had one that was a little more complicated. That in the theory he was studying was equivalent to this, but somehow in the more general setting, this is the.
Okay. But usually, like in Henselian, I remember that just reduction. If reduction has a simple root, that the simple root can be extended. Right?
Yeah.
So you just take this. Okay, sure. Okay.
So let me just understand the notation.
Yes.
P means it's a differential polynomial with
Mhm.
coefficient in O?
Yeah.
Okay.
And so one other definition I need, just because you don't really have to, I mean, it's important, but you don't have to worry about it per se, is that it will just show up as a necessary condition. That's why I'm telling you here. That if you're de-Henselian, then your residue field is linearly surjective, by which I mean every linear differential polynomial of this form has a zero. So this is just says you can approximately solve in some sense, you can approximately solve.
So you're sneakily packaging that in because having a simple root somehow maybe reduces to degree 1 things, but now you're also requiring that since it has a root upstairs, it's going to have a root downstairs.
So the one that you remember is there is a more direct analog of that says you assume the residue field is linearly surjective, plus then whenever you, so you can, this is just somehow more compact.
So this form of equation, it's actually not a special form. Like any linear equations is of this form up to constant. You just
The one is not.
You just have chosen to make it monic.
I have just.
No. You prohibit. So you prohibit 0 constant term.
Well,
right?
I mean that.
Is
but
there
that also
a special reason for that?
I mean, this also has a 0 at 0.
Yeah, it still has a 0, 0. Yeah. Okay. So you could actually have like.
Yes, I could have any. Yeah.
Okay.
But this is actually a useful way to think if you want to think of this equation as coming from upstairs, because upstairs in the valuation ring, you can't necessarily divide by the constant coefficient. So down in the residue field.
I see, but it's still divided, right?
Sure. In little k you can.
Yeah, in little k.
Yeah.
But if you're imagining this equation as coming from O, then this is worth emphasizing.
Oh, yeah, that's true. Yeah. Thanks. Yeah. So I mean, I just
So constant terms are invertible.
In little k is invertible, right?
Yeah.
Little k is a field. You mean that it's invertible?
You mean any element that's in O that is invertible has valuation 1 or valuation 0, right? It's not strictly bounded by 1. It's equivalent to, or not equivalent, it's asymptotic to 1 or something. Right. So what about this?
So the equation is considered as asymptotic equation?
We haven't seen that definition
I
yet.
don't know. I don't know what that means. Yeah.
Well, I mean, you interpret one as asymptotic one. I mean, when the constant term.
Just differential equation in differential field, right? I mean.
Okay.
Yeah. I mean, there's no valuation theory structure on little k, certainly.
Okay.
Yeah.
All right.
Yeah. So what about this uniqueness issue? So first of all, it's false in general. I mean, you can get continuum many maximal immediate extensions. In some sense, and this is not like a really pathological example either. It's an H field, which is like some algebraic kind of analog of Hardy field. But really, in some sense, the problem is one that you identified, that the derivation on the residue field is trivial here. Whereas I didn't, so the point is being differential Henselian implies a non-trivial derivation on the residue field. So this is why I write it like this, actually.
Oh, really? How does it imply?
Because
in the Henselian, you're not assuming that P bar has a solution, you're just saying it's degree 1.
I see.
And it implies that the residue field has non-trivial derivation because of this one here being non...
Yeah, has to have solution, yeah.
Everything has to have a solution. Right. And so they conjectured that that was kind of the problem, essentially. That if you assume that your residue, if you start with a linearly surjective residue field, then you should get this uniqueness of maximal immediate extensions. And well, it was proven in some cases. But let me tell you about what happens in the asymptotic case. So the value differential field is asymptotic if for all non-zero elements of your field that are f and g that are strictly bounded by 1, then their quotient is infinitesimal if and only if the quotient of their derivatives is infinitesimal. So this is, in some sense, a very weak L'Hopital's rule. It doesn't tell you how close they are or anything. It just tells you, if one is kind of going to 0, the other one should be going to 0. But not at any kind of rate or anything. And one implication of this definition, of course, I write it in, it's slightly sloppy, but I mean, this should make sense everywhere. So in particular, the constants should be included in the valuation ring. which makes sense. The constant should be bounded. If you're thinking about Transseries and Hardy fields, constant should be bounded. And so then in the asymptotic setting, you do get this uniqueness of maximal immediate extensions. And I guess I didn't emphasize, what are the cases considered before? The cases were relatively more, so by we, I'm not sure who I mean, I guess me, my advisor, and his colleagues, and some other people, are more interested in the asymptotic setting because somehow it's the earlier case that I mentioned, monotone, is relatively well understood model theoretically. There's a much stronger interaction on the valuation and the derivation, but it has much less to do with these Transseries. Basically, has nothing to do with these Transseries and Hardy fields. So somehow, asymptotic is the setting that we're most interested in, and it's kind of, in some sense, orthogonal to the earlier settings considered.
Go back to the previous slide.
Yeah. Yeah. So the cases that had been known for before were for monotone value differential fields. That monotone just means, if you want to know, that the derivative of every element is bounded by the element itself. Like A prime is bounded by A for all A. And there was an earlier, a subclass of this where Scanlon had proven it as well. Yeah.
And PC here is you, right?
Yeah, I am PC, sorry. Yeah. And then this finite Archimedean rank thing is just, it's kind of a small, in general, we like to think about value differential fields with big value groups. So this is kind of a small example that essentially reduces to the monotone case. But if you have value group Z or something like that, you can do it. But that's not really what we have in mind. So then there was also this relationship between between henselianity and algebraic maximality. And like in the valued field setting, one direction is easier than the other. So if K is linearly surjective and your capital K is de-algebraically maximal, then you're de-henselian. This is not too hard to prove once you develop some general theory of de-henselianity. But the converse is false in general, even in this monotone case that is pretty well understood.
And it's this algebraically maximal that fails because you already convinced us that de-henselian implies linearly surjective.
Exactly. That's why I have this linearly surjective here, because it's a necessary assumption. If it's not there, you cannot guarantee that it's there. But in the asymptotic setting, where you have a different interaction, this L'Hopital rule, you do get that de-henselian implies de-algebraically maximal. Yeah, and the counterexample, by the way, is constructed from Hahn fields, so it's also not too pathological. The counterexample to the monotone case, to be, yeah. And again, this was first proven in the monotone case. In the monotone case, they assume K is de-henselian, asymptotic, and monotone, which is a very restrictive case. Again, by Aschenbrenner, Van den Driest, and Van der Hoeven. Okay.
Is it possible at some point to
Yeah.
put the definition of asymptotic and monotone next to each other?
Yeah, maybe I can just write it.
Thank you.
Yeah, the monotone ones are not really relevant to the talk, except in that they were, well studied first.
All right. Thank you.
What is an example of a monotone one?
Yeah, so you can, some kind of Laurent series field, or generalized Laurent series field, essentially. If you define the derivation in the right way. Just term by term, say. start with some differential field and
Oh, okay.
yeah.
You could also just take Laurent series with actual derivation with respect to the variable, right?
Yeah, I guess I wanted to say something with small derivation
Ah, okay.
also. But
Rational functions?
wait, it will not be monotone if you have to scale the derivation, right? Because, you know, if your first term is AT,
Yeah.
then the derivative of that will be A times 1.
Yeah, so. Oh, I
T, so it depends, yeah.
So-
Are you thinking of T as infinitesimal or
Okay.
or
got it.
infinite?
Yeah.
Anyway, there's some minor
Yeah,
issues around
yeah,
that,
yeah,
but
Yeah, okay.
yeah, I had in my mind infinitesimal, but. Right, okay, where are we? Yeah, differential henselizations. Right, what is a differential henselization? So it's a differential Henselian immediate extension that embeds into every other differential Henselian immediate extension. So, yeah, every valued field has a henselization, and they're unique up to unique isomorphism because they, their property is that, well, it's a universal property, not semi-universal. But what Aschenbrenner, Van den Dries, and van der Hoeven were able to show was that, again, under this linearly surjective residue field assumption, in the asymptotic case, you have a minimal differential Henselian, differentially algebraic immediate extension. And so I thought, this should be, this should have some embedding property, but that's what I was able to contribute was that, in fact, this minimal one can embed into every d-Henselian immediate extension. And what this uses is the previous result about d-Henselian implying d-algebraic maximality. Somehow, this, yeah.
So what's the difference between minimal and then the whole big thing
Yeah.
and just henselization?
By minimal, yeah, okay. Minimal, I mean with respect to differential subfields. So this, K has an extension L that is differential Henselian, differential algebraic, and an immediate extension, and it has no proper differential subfields that contain
The other
K.
one is to embed in the middle.
Yeah. So, I mean, of course, once you get this, by this you get uniqueness because you can embed
Right,
them.
right.
Yeah.
Do you really need the word immediate in item 2?
This is a good question. Yes. I mean, so the problem is, yeah, it is. So okay, but I don't need it in some sense. So I give this definition in general. What I show here is that it embeds into every asymptotic d-Henselian extension of K. Which, if you're working in the asymptotic world, that's totally fine. And immediate extensions of asymptotic fields with small derivation are asymptotic. But the problem is it's kind of obvious, that you can always reduce to immediate extensions when you're dealing with henselizations, but it's not so clear in the differential setting. Yeah. But it is annoying, yeah. Yeah, so just the summary. So in the point is that in the asymptotic setting, we get these three kind of general valuation theory theorems or analogs of them that we had in the setting of valued fields, which we don't get necessarily, or in certain other cases that are still of some interest, we do not get all of these theorems. And in particular, the second one is the most, important, I guess, in that the maximal immediate extensions holds for other classes, but the d-Henselian being d-algebraically maximal is the thing that's kind of specific to this bounded constants asymptotic case. And the de-Henselization follows from that. Are there any questions so far? I'm going to say a little bit more about part 2, at least some hand waving about it.
So I have
Yes.
general question. So, do you understand correctly that these results they're somehow aimed towards proving Ax-Kochen Ershov for
Yeah,
asymptotic values? So,
yeah. I don't want to, make any bold claims, but the naive goal would be something like two differential Henselian asymptotic value differential fields are elementarily equivalent if and only if their differential residue fields are, and their value groups with a certain induced structure from the derivation that, are. That would be the naive goal.
okay, and what's like the reason to want such a statement?
I don't know. The model theorist.
Okay.
Classification.
Yeah,
No,
classification.
you answered my
I mean,
question, I suppose.
one way that you can do it is, classification, but also you might want to get some kind of, understanding when these de-Henselian asymptotic fields have various model theoretic classification properties, and maybe from this principle and, a little bit more work, you can reduce it to the case of your residue field and your value group, which are usually easier to understand.
But beyond very technical model theoretic components, so if I have a system of ODEs, what can this do about it? At least something.
Well, that's not, I mean, you could probably say something, but
Could you give an example?
can I give an example?
Okay, maybe since this is not the end of the talk, we can postpone the
Yeah,
discussion by the end of the talk.
No, you can't?
No?
Okay. I mean, from a model theorist, it's not really my motivation, so I haven't thought about it too much, in truth. Is this a satisfactory answer for now?
It's an answer.
It's an answer, okay.
Just to remind myself, actually, so all these results are about small derivation.
Yes, everything here is about small
So
derivation.
in other words, when you say it has a de-henselization, you mean it has a small one.
Yes, the de-Henselized,
I mean,
yeah.
the small derivation.
Yes, in order to be de-Henselian, it has to have small. I mean, it's part of the definition in
Part
some
of the
sense of
definition,
small.
right? Because everything has that.
Yeah.
Okay.
So
Does including the small derivation form some kind of a model theory language? I mean, in other words,
Certainly first order property.
I mean, it's a universal property in the language of value differential fields.
so you might as well put it as a separate model theory.
I don't know what you mean by that.
Well, I mean, it's like you have a theory of differential enclosed fields, so you have a theory of small derivation.
Like a theory of value differential fields with small derivation. Sure, yeah. So
That's what we're looking
that's,
at.
this is, kind of going on in the background is trying to develop some, study the theory of asymptotic value differential fields with small derivation. Mhm.
So what would be the signature of that theory?
Just, the normal language of rings, so plus and minus and times, 0 and 1. You'd have the derivation,
Right.
and
But how do we express that the O ring? I mean, the O is small O is closed under derivation.
so and you would also have the. So this is what I have in mind, and this dominance relation to the valuation. And then you can just say, something is bounded by 1, for instance. Or, whatever you want to say, you can. I mean, the small derivation just says, if you're bounded by 1, then you're strictly bounded by 1, then your derivative is strictly bounded by 1.
So the derivation can be recaptured from this dominance.
Yes.
Yeah, the dominance is the same thing as the valuation, but you do really need the the binary relation. I mean, this is generally true in valued fields as well, for certain model theoretic reasons. But Yeah. So, in some sense, everything boils down to this key property of the Henselian asymptotic fields, which is that given that a differential polynomial of order r doesn't have r plus 2 distinct zeros in a certain configuration, and is a little bit technical. I don't want to go into what the configuration is, but somehow everything boils down to this configuration. And just as a short point, you can from that argue quickly that every differential polynomial that has this degree of p bar is 1, and you have an immediate extension, then p must have the same bounded zeros as it had originally. And so this is this is necessary, right? Because if it had new bounded zeros in a differential, if you consider a differential-algebraic extension, then if it had new zeros, what am I saying? This is necessary as stated, because if you consider some immediate extension where it has new zeros, then that would generate a differential-algebraic immediate extension, a proper one.
Is it possible to describe the certain configurations for, say, r equals 0 or r equals 1? No is a fine answer.
So r equals 0 is not very interesting.
I agree.
Yeah.
But still, can you say something?
The configuration for r equals 0 is really that they're distinct, and it has this. So for r equals 0, say. And there exists a G with y1. So, you can always find such a G, and the degree of P of yi plus g y. So if you make this kind of change of variables, where you shift by this guy that is kind of, telling you that they're at least that close, then you should have degree 1 in the residue field.
Okay, thank you.
The other condition, there's another condition. This is my picture of a valued field in my mind that I have. It's kind of like a function from gamma to, it's a function that takes values in little k and from elements of gamma.
Okay,
right?
so sort of meditating on a Hahn field?
Right, exactly, meditating on the Hahn field. In some sense it captures all the additive structure, right? But it doesn't necessarily capture anything else. But, it's helpful for dealing with certain pseudo-Cauchy sequences. Basically, they all have to y0, y1, y2, they have to kind of lie like this along the line. So this, to be clear, this is an element of the field, right? Each path is an element of the field.
Yeah.
And they have to lie like this, so that this one, these two are this close, and then the next two, they're getting closer and closer. They're kind of, in some sense, approximating some element in an extension. And you can make this precise in evaluation theory. But
Okay. Thank you very much.
yeah. Right. So what you want to do is you take some f and some immediate extension, proper immediate extension, I should have said differential-algebraic, proper immediate extension. Then by some general kind of theory about pseudo-Cauchy sequences, it's the pseudo-limit of a pseudo-Cauchy sequence. Whatever that is, it's the right notion of Cauchy sequence in valued field. Okay. Basically, it's that picture. Like a pseudo-Cauchy sequence is the limit of, if I draw infinitely many more things along that line, they should get closer and closer together. What they do is I have a whole lot more, I mean, some ordinal length sequence, they define some kind of cut. Whereas all the, I would like to fill this in with, continue this with an element that actually is a pseudo limit. But there could be many of these because this value group is very non-Archimedean. So there could be lots of different things. It defines some kind of cut in the. And you can find a minimal differential polynomial of this sequence, by which I mean P of f kind of pseudo converges to 0 in this sense. What this means, I guess you should just think P thinks that there should be a 0 that is the limit of the sequence, and you can arrange that f is actually a 0 of P. And then the third step is to use this sequence to find infinitely many zeros in the configuration as above. So yeah, this key property is built in such a way that, when you go along the sequence, if you could get that this degree equals 1 eventually, you would be able to find infinitely many zeros in this configuration, which is the problem. And so what can I say about this? The third step is the really hard step.
What was the third step?
The third step was to find the infinitely many zeros in the configuration. Yeah. Because it's very vague, so it doesn't,
Proving
all
the
the-
configuration is impossible is not that bad.
Yeah, proving, the configuration, you mean this key property, is not too bad at all. No, this is like a short, you just develop some kind of basic general theory and you can do it. It's not very hard. And similarly, it's not too hard to get from there to here. But somehow it's much harder to get to the general setting. And so, yeah, the key property is basically when you're in this setting, the degree of p bar as you go along the cut is 1. So somehow, eventually, if you go far enough along in your sequence, p bar looks quasi-linear. Yeah. I mean, I am being vague, and I apologize. So, yeah. But yeah, essentially the.
What do you mean by the degree of p bar in the cut?
Yes, this is a thing that I have not defined.
Okay.
But
Okay.
essentially, it means you consider degree of
Oh, I see. Okay.
this
Yep.
for sufficiently
Yep.
far along elements of your sequence and sufficiently chosen G. Yeah.
But like in this proposition, you implicitly assume that P is minimal, right? As you have chosen it.
Oh yes, I do assume it's minimal. Sorry. Yes.
Okay.
Yes. Yes. Yeah. Yeah. The proof is technical and kind of the most interesting thing, but somehow the thing I'm also that you might be most interested to hear about, but also I'm least qualified to explain, is this differential Newton diagram method, which is, so the differential Newton diagram method that I use is based on a differential Newton diagram method for Transseries that was originally developed, as I understand it, by Joris van der Hoeven, which was adapted to the H-field setting by Lau and Matthias. And my understanding is that Joris is really the only one who claims to really understand, the details of what's going on. So, I can read it and, adapt it, but, yeah. I can say something, but it's, again, a little bit vague, so maybe I will not. I don't know, it will be.
So you should talk a whole lot about it because that's how you figure stuff out.
Yeah, this is true. Yeah. But the problem, of course, is that the valuation of f doesn't really control the valuation of f prime, right? So in the monotone case, it does. When I plug an element into a differential polynomial, I know what the terms do.
Yeah.
But when I plug it in the asymptotic setting, I don't know what the terms do. And that's what makes it much harder than the ordinary valued field setting, because you just have one term of each degree, and you can do things kind of. Okay, you guys all know about that, but somehow, I come from slightly different motivation, as you have seen, but somehow trying to do valuation theory for differential fields, in my perspective, the derivation is really making my life difficult, and not that it, which means I really get to commiserate with my Calc 1 students. I don't think they appreciate it, but it's honestly felt. So, okay, I think that's all I'll say for now. Yeah. Thanks.
Questions? Just again, possibly where things are constant, where not constant. So in all the theorems, the residue field is non-constant.
You mean the derivation is non-trivial?
Yeah,
Yes,
yeah.
Mm-hmm.
So, and do you have any plan how you could then apply these techniques for like Transseries or Hardy fields, or this is not what you want to do?
So, so I guess these things are already kind of known for Transseries, Hardy fields, but the terms are different. So there's a different generalization of Henselian that makes sense when your derivation is trivial, that they call Newtonian. Okay, anyway, and this differential-algebraically maximal you can replace by only asymptotically differential-algebraically maximal, in the sense that you only consider asymptotic extensions. And so these things are already kind of known in that setting, but with slightly different terms. What my secret goal, I guess, would be to unite so you can define this, so this degree of P bar is like this dominant degree. They define some more technical Newton degree in terms of dominant degree. My secret goal would be to combine both theories, because they can define Newton degree for any value differential field with continuous derivation. Maybe modulo the value group has no least element, least positive element, or something. But like up to some minor assumption like that, the goal would be to unite them together. But I think this is maybe more ambitious than I can do in a thesis. So.
Okay.
Yeah.
Thank you. Other questions? Well, let's thank speaker again.